We integrated from left to right, start to stop. We have to think about the cross section, which all of those were circles. And so we integrated the area of that cross section. So remember, area is pi r squared. And because the radius varied depending on where you were, we had to have a formula for our radius. Now, sometimes you may not know a definite left and right hand point, but you might know a bottom and a top. So in that case, we are going to integrate with respect to y. And we kind of saw this with our areas even. Sometimes our areas, it was hard to do in terms of x, so we kept it in terms of y. And if we're doing the y's, you have to know the bottom and the top. So let's take a look. I think, is this where I left off? Find the volume of the solid obtained by rotating the region. Y equals x cubed. What's x cubed look like? So x cubed looks like this. We're drawing a rough circle or rough graph. Y equals 8. What kind of line is that? Horizontal line. Yep. So y equals 8 would be this horizontal line. X equals 0. What's that? Vertical line at 0. Okay. When I say it's bounded by that, I'm talking about the region in between all of those. So I'm really just looking at this little piece right here. Is that okay with everyone? And if I start rotating that around the we're rotating around the y-axis this time. So Friday, all of them were going around the x, and so we had the left and the right. But if I start rotating this around the y, so it's going to spin over here. So we're just getting something like this. Do I need to pull up my visual that I was doing the other day, that website? Okay. Do I have a clear left and right hand point here? It kind of varies depending on where we are. You know, if we're down here, this is the left and that's the right. But as we go up, the left and right change, don't they? So because I rotate around the y, it's probably going to be easier to do this in terms of y. What is my smallest y value? And what is my biggest y value? 8. So when I'm thinking about this, if I do y as my variable, then my cross sections are formed here. So if I'm looking at this cross section, that's what we're integrating, all those different pieces. It's still circular. So when we integrate, we do pi times the radius squared, but this time 0 and 8 are y values, so my variable has to be y, that has to be a dy at the end. The radius of this is from the center out, so we're measuring our radius from the y-axis out. What's the equation of this line? Y equals x cubed. Can I put x cubed in here though? No, because I said everything had to be y's. So how do I get this in terms of y? Yeah. X is the cube root of y. You just saw that. When you invert from 0 to 8, you can take out your pi if you want. Cube root is like a 1/3 squared, so that's y to the 2/3. Add 1 to the power. So 2/3 plus 1, 5/3. So we need a 3/5 in front. So it's like 3 pi over 5. You put in 8. Cube root of 8 is 2. 2 to the 5th. 32. Minus, put in 0, cube root of 0 is 0, to the 5th is 0. So you get 96 pi over 5. So typically, if you are rotating around the x-axis, you are going to have your variable in terms of x. When you're rotating around the y-axis, we're going to do it in terms of y. Is that one okay? All right, so this is just kind of a summary of what we've been doing. When we are integrating these around the x-axis, if you're taking a curve and spinning it around, you're getting a circular shape. And so we know the area of that is pi times the radius squared. And we kind of noticed Friday, the radius is always the function. So that equation that you're given is your radius, as long as you're rotating around an axis. If we start rotating around like vertical and horizontal lines, that changes. But if we're doing it around the axis, the radius is the function. So this is what we've been doing in all these problems. This is called the disk method. So I was kind of making you think about what the radius would be, but this is just a summary of that. So let's take a look at this one. Find the volume of the solid formed when the region enclosed by the curves y equals x and y equals x squared is rotated around the x-axis. What variable do you think we're going to do this in terms of? How come? Yeah, remember I said if you're rotating around the y-axis, you'll probably do it in terms of y. If you're rotating around the x-axis, you'll probably do it in terms of x. Let's see. Let's draw a picture and see if that helps. Y equals x. What's that? Yeah, that's just the identity. Y equals x. Okay. What is y equals x squared? Crap. All right, so I want the region enclosed by those. The region enclosed is right here. Right, so that is the little thing that we're rotating. So I'm just going to erase these other lines because that's almost confusing. If I start spinning that around the x-axis, so for me to think about spinning, I usually think of it as reflecting first. If I just flip this thing over the x-axis, comes down here, and we're spinning it, so it's all connected. Okay, can you guys visualize what this shape is? It's like a cone. The difference is this one is hollow in the middle because we had this one little piece that we're rotating. Versus the others, we are always doing just like between that and the axis. And so when you spun it, it was a solid. This one's hollow in the middle. All right, so the question is, do you have a definite bottom and top or a definite left and right? Left and right. So that's why when we're doing in terms of the x-axis, it's usually easier to find a left and a right point. So we're going to do everything in terms of x. To find those points, we really need to know where these curves meet. So the question is, when did x equal x squared? So x squared minus x is equal to 0. So I'm going to integrate from where to where? 0 to 1. Of pi times my radius squared, and we're doing it in terms of x, so that's a dx. All right, this one is a little bit different. If you think about this, if you take a cross section, what kind of shape are you looking at? It's still a circle, but what's true about this circle? It's hollow in the middle, so it's more like a washer or a donut. Okay, so to get the radius, we have to think, okay, that's from the center all the way out. Which curve is all the way on the outside? X was on the outside. So we have to think about it essentially as like the outer one minus the inner one, if we're going to get just the part between them. So the outside one squared minus the inside radius would only take us to the bottom curve, which was x squared squared. So I set this up all as one integral. You didn't have to, so if it makes more sense to you, you could think of it, okay. So this is just kind of a side note, you don't have to do this. But you could think, all right, if I were doing the outside one, that's pi times x squared. And you have to subtract the inside one, so we get that hole in the middle. So if you do the inside one, that was the x squared squared. So I just put it all together in one big integral, but you could do two separate ones. The area, or the volume of the outside part minus the volume of the inside part to get what's between them. Other questions in terms of that? So now, that's the hard part. We have integral from 0 to 1, you can take out the pi, so this is x squared minus x to the 4th dx. Antiderivative of x squared minus antiderivative of x to the 4th. Okay, so if I put in a 1, I get 1/3 minus 1/5. Minus, put in 0, you get 0. 2 pi over 15. So this was kind of a lead up into the second type of problem. The first one is when we just have a single curve being rotated around the axis. And then that was what's called the disk method. We just do the integral from a to b of pi times the function squared. If we have two things being rotated around the same time, then what that does is it causes the inside to be hollow. So how do we find the volume? Yeah. Right, we had to do the outside one F minus the inside one G. So that's what's called the washer method. So it's pi times the outside radius squared minus the inside radius squared. So let's try a few more. Find the volume of the solid obtained by rotating the region in example 6a about the line y equals 2. Alright. So that was the y equals x and y equals x squared. So we know those two together created this little region. Where is the line y equals 2? It's a horizontal line. We know this met at 1. So, best suggestion I have if you're trying to draw these, think of it as a reflection first. So if I reflected this across that line, here, here, we have a line on the inside. So we're getting something like this, but we know it's kind of like a Christmas tree stand or some kind of cone, hollow in the middle. to integrate with respect to x or y? Y equals 2 is a horizontal line. The x-axis was a horizontal line, so as long as you're rotating around a horizontal, it's probably easier to go in terms of x, because we have a left and a right, but my top and bottom change depending on where we're at here. So if you're rotating around a horizontal line, keep your variable x. If you rotate around a vertical, make your variable y. Something we're going to go with dx. Okay, if we're doing it in terms of x, we do left minus right. What is my leftmost point? Still 0, and my rightmost point was when x is 1, so that didn't change. But what changes here is the radius. If you look at a cross section, so if I slice this thing, I'm still getting a circular shape. But what happens is it is hollow in the middle. So you get something like this. When you are measuring your radius, it's no longer just the function. The radius is from this line, the 2, out to the curve. So which one's on the outside here? The x or the x squared? The x squared. So the radius would go from, we think if it starts at 2, and this is x squared, what would you do to find the distance between them? So this outside radius is 2 minus x squared. Minus, then we think about the inside one. So the inside radius, again, starts at 2, but it goes down to this line. So this would be, that line is x, so the distance between the 2 and the x would be 2 minus x. And we always do the radius squared. So that was a little bit harder, but because we started at a horizontal line, we have to think our radius is the distance from that horizontal line to the curve. So we just subtract them. Are you guys with me there? Any questions?
Where did the 2 come from?
In the problem I told you, this time we were rotating around y equals 2 instead of the x-axis. So that moved everything up 2. Other questions? So now that's the tricky part. Now we need to integrate. I would probably choose to multiply some of the stuff out first. So if I FOIL that, I get 4 minus 4x squared plus x to the 4. Plus you.
Oh, thank you.
Minus, this would be 4 minus 4x plus x squared. So if we combine like terms, we get x to the 4th minus 5x squared plus 4x. Start derivative of x to the 4th, 1/5 x to the 5th, minus derivative of x squared is x cubed, so 5 times x cubed plus 2x. 0.
Is that 2x squared equals 2x?
So I want to take that same region, but this time I'm going to rotate around x equals -1. So my region, we have the y equals x, y equals x squared, and that one x is 1. If I rotate x equals -1, so -1 is the line we're rotating around. X equals is a vertical. So hint for drawing these, think of it as a reflection first. So if I flip this over, it would go here. This point would go here. Line is on the inside, curve is underneath. And I know you really have to use your imaginations here because my artwork is not great.
So how do you know where to start our next drawing? Like wouldn't we start at normal? Like I get it, like
Okay.
rotating around.
Think of it as a reflection. So this point is 1 away from that line. So if you reflect it, it would go 1 away the other direction. So this point is 2 away from my vertical line, so it would go 2 the other direction.
So we just reflect it from wherever the x equals.
All right, this time I rotated around a vertical line. What does that mean? We're going to do it in terms of y. Because we no longer, can you easily tell me the starting and stopping point for x? No, but the y's we can. And when I take cross sections, we want horizontal pieces of this, right? So if we're rotating around a vertical line, we're going to go in terms of y. So this will be a dy. Okay, what is our smallest y value? 0. Our highest point was when they met. That was 1. Because y equals x, so y equals 1. Okay. Now we have to figure out how to do this part. So if we think about a cross section, it's still circular. It's this piece here. So it is measured from the -1. So we have to think outside minus inside. So which curve is on the outside? The x squared. So we have to go from the -1 to the x squared. How do you do distance between those? Okay. Squared. Except we said it had to be in terms of y. So can I use x squared? Okay. So that curve was y equals x squared. So if you solve for x, that means x is square root of y, or y to the 1/2. So the -1 minus the square root of y squared minus, now we do the inside. So the inside, it's from -1 out to what line? Y equals x. So -1 minus, we can't use the x, but y is equal to x, so we could do -1 minus y squared. Okay. That's the tricky part. Now, before we integrate, we probably want to multiply this all out. So if I square that, -1 times -1 would be 1. Plus radical y plus radical y, so that would be plus 2 radical y. Negative square root of y times negative square root of y is positive y. For this one. Alright, combine like terms. So the ones cancel. So we have a 2 square root of y, or I'll write that as 2y to the 1/2. Positive y minus 2y, so minus y squared. Antiderivative of 2y to the 1/2. Becomes a y to the 3/2, so you need 2/3 in front times 2 that's already there, so 4/3 y to the 3/2. Antiderivative of y, 1/2 y squared. 1/3 y cubed. So I know it's a little more challenging when we have to subtract them, but especially if you are no longer rotating around the axis, because you have to put a little more thought into the radius, it's not just the function. But big things to remember, if you rotate around a horizontal line, your variable should be x. If you rotate around a vertical line, everything needs to be done in terms of y. So, stopping here today, there are 4 problems I want you to add to the 2 you've already done. Tomorrow we will finish this and add to that one more time.
Oh, is there a test gonna